Today we're starting section 3.3. There it goes, which is multiplication and division of whole numbers. And it's going to feel a lot like 3.1. Okay? So we're not going to do a lot of actual multiplication and division. This isn't the algorithm section like in 3.2 that you just did. This is the conceptual part of understanding why things work. Okay? So to start with, we're taking a look at what the definition of multiplication means. So this is multiplication of whole numbers. So if you have numbers, whole numbers A and B, and there's an n that's not equal to 0, and you have n times A, this means you have A, that written right, plus A n times. And if n equals 0, then by definition we say that 0 times A is 0. The definition doesn't really work if n was 0 from the first part right now. That's why it's a second space. Okay, and then if we have finite sets A and B, so do you remember what finite means?
It has like an ending, start and end.
So it's kind of, so if we were to count the numbers, we would have a stopping place where we stop counting. Does that sound like what you're describing? Yeah, you can think of it that way. It may be really, really large, right? So you may not physically be able to or want to count these sets, but you could in theory, right? There's an ending place to stop the counting. Yeah, you can think of it that way. So if we have n of A equals A, do you remember what this notation means, n of A? It's a cardinal number. It means the number of items. So we have A items in set A, and we have B items in set B. Okay? So if we have that set described, then when we talk about A times B, what we're actually talking about is the cardinality of the Cartesian product, which we encountered before. We've seen this definition before, but in a slightly different context. And another way that you can describe this is basically that if we're talking about multiplying the number of items in set A, because that's what A, little a, means, times the number of items in set B, that is the number of items in the Cartesian product. And that's actually the description we saw before, exactly. So the first one's just a little bit different notation. Okay, so what you might remember is where we headed after definition in section 1 is we started talking about models for doing things, right? So in particular, like when we did subtraction models, we had this idea of takeaway or comparison or missing added. Those were different models for subtraction. All subtraction, but from a different perspective. We're going to do the same thing now with multiplication. All right, so the first one for multiplication is repeated addition. Jessica takes 3 tests every Friday. After 4 Fridays, how many tests has she taken? Too many. Thank you, Kate. Yes. Too many. All right, so what could we do, or how is this sort of being represented? Well, it's being represented like we're actually repeating addition. We have 3 on Friday number 1, and we have a 3 on Friday number 2, and a 3 tests on Friday number 3, and 3 tests on Friday number 4. This is 3 times 4, because we're repeating those, in this case, tests. And of course, the result is 12. Okay, array model is one of my favorites. An array model, an example of one, is Marty's baking cookies. He's able to place the dough 3 cookies wide and 6 cookies long with his pan. How many cookies will his pan hold? Now this says used for sets. So we're going to see another model that looks very much like the array model, but it's used for measurement instead. Okay, Okay, so sets, if you'll remember, are objects where we count the whole object. Okay, so it wouldn't make sense to sort of talk about half a cookie in cookie man. We don't do it that way. So these are objects that we have physical objects of when we're doing an array. So if we're taking a look at drawing a picture or something that represents what's going on, I'm supposed to have it 3 cookies wide. I'll add a purple cookie today. And then we're going to, I'll clone this, 3 cookies wide. So I'm going to draw it that way because I've got more space. And then it's supposed to be 6 in the other dimension. The other dimension is supposed to be 6 long. Okay? So I need this to be 6 long. Alright, so there's my array. It's not perfect, but you get the idea. And this is still the same kind of a multiplication problem, right? I've got 6 times 3. And how many is that? 18 cookies. This was 12 tests, by the way. So we have 18 cookies from an array model. It's not a repeated addition description, right? It's not like I made 3 cookies today and I made 3 cookies tomorrow, I made 3 cookies on Saturday and 3 cookies on Sunday. It didn't do that. Because that would be repeated addition. This is an array. I've got a physical picture that looks like this going on. Alright, the next one, this is area model used for measurement. This has almost the same feel to it as the last one, except it's used for things that are measured, like distances or lengths. Okay? So here's an example. We've got Alexis, she's planting a garden. She has a space that's 5 feet wide, 7 feet long. How much area does she have to plant? So if we draw this one, we're going to draw it in what shape? It's a rectangle. Get the right one. Something like that. So this is 5 feet. And this is 7 feet. And if we wanted to continue to draw the picture, we could break it apart by its feet, kind of like the last one looked like with the circles. So I could take some lines and I could actually split it apart. Okay, so it's not perfect, but pretend it is. So there's 5 equal feet long, or wide in the description, and then I need 7 feet in the other direction. Even worse. Sorry. If you were to count the little squares, the little rectangles inside of there at this point, because they don't look like squares at all, you would get 35, right? Alright, so just for a moment, what would I write for my units on that? Because this is a little different. It's square feet or feet squared, yeah. Simply because I'm multiplying feet times feet. So the dimension would actually be feet squared. All right. So, I want you guys to stand up and move around. Get your groups. You guys did this once before for me, right? Get your groups, please. Does everybody know who the partners are? I think everybody's here today. No, we have one gone. Tiffany's gone. Anybody else missing a partner? Okay, once you're in your groups, what you're going to do is create a word problem for each one of these examples. Something that looks like repeated addition, something that looks like an array, and something that looks like area. Okay? Be prepared. We want to share one of them with us. Alright? I know, it's exciting. So go ahead and take a few minutes. We're not going to take a ton of time doing this, but you're going to write 3 different word problems. Okay, so there are 6 groups of you, and there are 3 problems, which means I want you to look at your problems, because I'm going to ask that we get two examples, at least two examples for each one of our different models. So repeated addition, what do you have? What do you review your model? Hannah.
Said if someone buys 2 pairs of shoes each week for 8 weeks, then how many pairs of shoes will they have?
There you go. That'd work. That's repeated addition. What else?
Every Monday, I drink 2 cups of coffee. How many cups do I use?
How about an array? You know, an array model.
Nicole is planting flowers in the garden. She plants 20 flowers wide and 8 flowers long. How many flowers does she plant?
Excellent. What else? Another array model. One more.
She can fit 5 pairs of shoes across her closet floor. Across the closet floor, and 5 pairs of shoes down the closet floor. How many pairs of shoes can she fit in her closet?
Very good. It's like shoes. All right, we have 2 groups left for the area model. So one of you want to tell us what you have for area model?
Joey's making a fence sign, 4 foot long and 6 foot wide. How much area is Joey's fence sign?
I said Abby's playing soccer. The field she is playing soccer in is 200 feet wide and 100 feet long. How big of a space does she have to play with?
All right, so we got the idea of the different models, yeah? Okay, so if you want to twist your desk a little bit to see the board better or move around a little bit to see better, that's fine. But you don't need to move, per se, back to where you were before. You're fine as long as you still Are you okay with that? Alright, as long as you are safe. That's good. Okay, so I've got people on the very edges. So Katie, can you see the board? And Bailey, you can work. Excellent. It's Friday, right? All right, we're going to talk a little bit next about the different properties of multiplication. We've seen these properties before, yes? But we've seen them applied to what? Addition, and we talked about how almost none of them apply to subtraction. All right, so we're going to take a look at what happens when we do multiplication. All right, we do a closure property with multiplication for every whole number, A and B. A times B, or we can write this A, B next to each other. That's fine too. Okay, different ways of writing it. Is a whole number. Okay, remember the whole idea about closure is you take 2 objects that can be described in some way, and when you combine them with this operation, they can still be described in that same way. Okay. Now that doesn't work for everything. You guys have seen some examples where closure doesn't work, right? So can you think of a way to describe, this is multiplication, whole number times whole number is whole number, right? 5 times 3 is 15, 5 3 15, all whole numbers. Can you describe a way to limit what you're, can you create a set that's limited, not all the whole numbers, so that when you multiply them out that doesn't work? Or that it does work? Okay, so natural numbers is almost like whole numbers. We're just eliminating the number 0. So something a little bit more restricted is what we're looking for.
But like the count numbers isn't only 1 to 10.
Well, counting numbers can keep going beyond 10. Right? So counting numbers don't stop either. So counting numbers and natural numbers, they don't stop. Now, if we defined a set that was simply the numbers 1 through 10, this wouldn't work, right? It wouldn't be closed, because if you take, for instance, 5 times 3, you get 15, and that's not in the set 1 through 10. So you can think of it that way. Is that where you're kind of headed with that?
Yeah.
Okay, if that would work. We're going to get to rational numbers later, but rational numbers have this property too, where if you multiply 2 rational numbers together, you get another rational number. We do rational numbers in math too, though, so we're not going to get quite that far in this particular class. That's okay. What happens if we had the numbers that were even numbers?
6 times 2 is 12.
And is that even? So are the even numbers closed underneath multiplication? Even times even always equal even? It does. Yeah, we actually have a closed set when we do even. What if we do odd numbers?
Is 7 times 7 is 14.
You're thinking about addition. So if we did addition, how about, that was my next question, and I was headed there exactly after this. So let's go back to multiplication, but I'm gonna get to addition actually, because that's where I was headed with this, yeah.
9 times 3 is
9 times 3 is 27.
27. Sorry.
Yeah, so we're still odd, right?
3 times 3 is
You guys went active, man. Alright, so if we multiply, that's the operative word, multiply odd times odd, it is odd. So odd numbers actually have this closure property too. But if we do odd plus odd, which is all three examples that you ladies have given us, that one wouldn't work, would it? Okay, so again, this closure property doesn't work for everything, but it does work for some things. And it works for whole numbers. So whole number times a whole number is a whole number. Do you remember what commutative means in general? You can flip something around, the order, right? The order changes. And this works here too. So for every whole number A and B, A times B equals B times A. That is actually a third way to write this. I should write it up here just for fun. I should dot this way. All right, you guys know that. 5 times 3 is 3 times 5. It's the beauty of flashcards, right? Once you know some of the tables and you get to the very end, you've already done all those multiplication tables except for like 1 or 2 new ones. Okay? So this is a commutative property. Associative property, what did that have going on? It's the groupings with parentheses. You're doing the picture in the head in there, right? With the parentheses, yeah. So we see parentheses, but it's about how things are grouped within the parentheses, which is the real key of what the parentheses are doing for us. So we have 3 numbers here, A, B, and C. So with the associative property, what it says is that if I group the A and the B together and multiply by C, that's the same as grouping the B and the C together with the A on the outside. Notice the order still is A, B, C. Order didn't change at all. What changed is what was grouped together inside the parentheses. So the associative property holds, so that's good. We have a few more. Identity property. Now, I was really picky on some of you guys' homework that I handed back last class period. Because some of you, when you're identifying properties, told me that you had an identity property. And I put in an extra word. Do you remember what it was? Additive. Because an additive identity is different than a multiplicative identity. So what is the additive identity? 0. The number, the additive identity, the number is 0. Yeah, with addition. So if I were to add the number 0 to anything, it doesn't change the value. But now we're looking at multiplication. So for multiplication, the multiplicative identity is the number 1. Right? And the reason that that works is because 1 times A equals A times 1, and that is the A that I started with. So that's what has to work for the identity properties. The order has to be commutative. We have to be able to do it in either order. And this time we're working with multiplication.
So it only works pretty much like the number 1.
The multiplicative identity is only the number 1. Yes, there's only one multiplicative identity 1, just like there's only one additive identity 0. Yes. All right, we also have a 0 property. This is new. We didn't have this before. A 0 property says that if you take 0 times any number, what do you get? 0. And again, it doesn't matter the order of the multiplication. So that is a 0 property, multiplication. We didn't have a 0 property before. We also have a distributive property. Many of you really wanted distributive properties before, and I said, hold your horses. We don't have enough operations for that yet. Well, we do now. And there's 2 different distributive properties. There's distributive property over addition and the distributive property over multiplication or over subtraction. So the distributive property looks something like this. If you have A times B plus C, so notice there's a combination of multiplication and addition going on. You tell me, because I know you know, what does this equal? Right, A times B plus A times C, or AB plus AC. And sometimes you see people draw a picture like this when they're describing it in algebraic notation. I'm going to draw you one other picture in a minute, but let me do the subtraction property first. So the subtraction property would still have A, B, and C. What's going to be different? Yeah, it's going to be B minus C. So what's going to be different in the simplified out, multiplied out version? Yeah, you're going to have a subtraction sign between them as well. There's another way to describe this, and I'm going to do it with an area picture because it works as well as anything. And just for fun, maybe we'll do it with some numbers. Let's say that we had 4 times 3 plus 2. And so I'm trying to justify that this really is 4 times 3 plus 4 times 2. I'm just putting numbers in to justify the property. There's nothing special about the 4, 3, and 2. I just want something that I can draw a picture for. So let me show you what I mean by my picture. I'm going to draw an area model picture. We'll go with that. Alright, so this is 4, length 4 over here. And along the top, I'm going to have a length of 3 and a length of 2. Okay. So in an area model, 4 on one side, I have a 3 portion on top and I have a 2 portion on top, kind of like a number line. And if I broke this apart into 2 pieces, so imagine taking that sign, Len, that you talked about in your example and breaking it into half, not in the sense that it's half, like equal halves, but breaking it apart into 2 pieces. So you're breaking the rectangle apart into 2 pieces. You guys know how to find this area, right? That's an area model. It says that I should be getting 4 times 3, which is 12. And you know how to find this area. What is that area? 8. And notice that's the 12 and the 8 that you get when you distribute. Picture, and that's what you're doing. You're breaking it into pieces. And of course, it's the same thing if you were to take the whole value, 3 plus 2, which is 5, and multiply that by the same 4. All right, we're going to do one more slide today. The slide we're going to do is on properties. So let's just see what we've got. We're going to identify which property of whole numbers is used in each of the descriptions or each of the examples. How about the first one? 5 times 4 times 0 equals 0. What property is being used?
0.
That is the 0 property. How about the second one? I've heard 3 answers. Almost all 6 of them. Okay, so let's take the first one I heard and we'll discuss whether it works. Is this distributed? No, it is not. Why not? Distributed property should have inside the parentheses either an addition or a subtraction. There's no addition and subtraction in this problem, right? So distributed property is off the table. Now what? I think I heard somebody say associative. Is this the associative property? Got some no's going on. Why is it not the associative property? It's the same stuff inside the set of parentheses, right? The same numbers are in the parentheses as were on both sides of the equation. So this is not the associative property. Is this the commutative property?
Yes.
Why?
Because the numbers are just switched.
The numbers that are multiplied are switched. In particular here, the numbers that are switched are 3 and 4. So this is the commutative property. Okay, how about the third one? Associative. Why? Because the groupings are different, right? The grouping on the left is 3 times 4, and the grouping on the right is 7 times 3. But notice the order of the numbers stays constant, doesn't it? That's part of the associative property as well. There's no order changing of the numbers. This is 7, 3, 4, and it's still 7, 3, 4. So this is the associative property. Okay, how about part D?
Is that the identity property?
It is the identity property. Why?
Because it's multiplied by 1.
And then it
Like,
didn't change.
the same thing.
You got it. So this is the, what kind of identity property? It's multiplicative. So you have to write that phrase because it's a different number than the other identity property you have. This is the multiplicative identity. If you leave the word property off, I'm not going to squawk. It's okay. How about E? That's distributive. If you want to be real specific, I think your book will do this. It'll say the distributive property over addition, because you've got addition going on. As long as you get the distributive part good. How about F? strange. What's going on? It is distributive. What is being distributed? Careful. It's the 1 plus 2 that's actually being distributed to the 3 and the 4.
So that's like the foil.
You would, right? Yes. Yes. What you're remembering from FOIL is a distributive property. So this is the distributive property as well.
Are you gonna take off this spelling? Like for multiplicative?
The only one that I really worry and take off spelling for typically is commutative because you guys turn it into other words that mean different things. So some of you actually did that on the last time I collected something. You turn it into commutative or something like that that actually has another meaning, which is a problem. All right, so please go ahead and take a look at some of this over the weekend. I won't be collecting on Monday because we're not quite finished. We've taken care of everything about multiplication. So not the group words, don't do that, but you can look at anything in that section about multiplication. We've covered that material. We're at division when we start